pole is actually larger than the corner frequency of the zero. Okay? So here, when we try to look at the magnitude response of the system here, I have here omega. I have here minus 90 degrees and minus 180 degrees. I can here mark the corner frequencies. The corner frequency of the zero is 1 over t, and this is going to be 1 over t is here, and 1 over alpha t is here, and I have 1 over t, 1 over alpha t is here. And let us try to now draw the magnitude response here. And here I have GC of j omega magnitude in dB scale. Okay? So here, when everything is much smaller than these corner frequencies, these terms are 1 and 1 here. Okay? So we see that if frequency is much smaller than the smaller corner frequency here, we see here that the magnitude should be 1. And here I have 0.1 over t, I have 10 over alpha t, and 10 over alpha t here, and I have 0.1 over t here. So we see that here, when the frequency is much smaller than 1 over t, the magnitude is going to be 1, which is 0 dB. Okay? And after this corner frequency, since we are still much smaller than the corner frequency 1 over alpha t here, this term is going to continue being 1. Okay? This will not contribute anything, but this thing will start to contribute to the magnitude. And the magnitude is now going to start increasing by 20 dB per decade positive slope. So it is going to increase like this until the second corner frequency. Okay? And afterwards here we are going to have the effect of this thing now, because we hit the corner frequency of the denominator term. Okay? And that is going to bring us minus 20 dB per decade slope additional to this. So currently I have plus 20 dB per decade slope. If I add minus 20 dB per decade slope to that, we're going to become, the magnitude response is going to become horizontal after that point. So we're going to have an asymptotic plot given like this for the phase lead compensator. And we see that for the phase term here, we see that here as we have here this term, when I look at the phase response here, we see that if omega is very small, then the phase is going to be equal to 0. Okay? Here I have drawn this in the wrong way. Because phase is always going to be positive, maybe I should show it in the following manner. So I have here my corner frequencies, 1 over t, 1 over alpha t, 10 over alpha t, and 0.1 over t. Phase is going to be equal to 0 if the frequency is much smaller than both of the corner frequencies. Okay? So when the frequency approaches the corner frequency 1 over t, since we are much smaller still than the corner frequency of this denominator, the phase is going to start increasing. Okay? Due to the numerator term. Okay? And here we are going to hit the corner frequency 1 over t here, and the increase can continue for some time, but afterwards we are going to get close to the corner frequency of 1 over alpha t term, which is going to make phase to get smaller and smaller, and we are going to get again 0 phase when the frequency is large. Okay? So this thing is the body plot of the phase lead compensator. I have GC of j omega here. This thing is going to be used to increase the phase margin of a control system. Okay? This positive phase is going to be used in our compensator design. So here we are going to be able to benefit from this compensator as much as possible. So I need to be able to increase the phase margin of a control system as much as possible by using this peak positive phase. And the reason that this compensator is called phase lead compensator is that its phase is always positive, and actually we are going to use this phase lead in order to be able to increase the phase margin of a system. If I consider a system with a control system with a body plot given like this, I'm making this up, okay? So here, and let us say that I have the following phase plot, okay? So here is my minus 180 degrees, and this point is our gain crossover frequency. Gain crossover frequency is the frequency at which gain crosses the value 1 or 0 dB. I'm going to look at what the phase is at that frequency, okay? And that phase plus 180 is going to be my phase margin for the system. Okay, so here I see that, let us say the phase is here is at minus 170 degrees. Then what is the phase margin of this control system now? It is 10 degrees of phase margin, which is not going to be sufficient for us. Phase margin is going to be a performance measure determining the damping ratio of the system that we would like, and we would like it to be much larger. Okay? Then what we are going to do is that we are going to try to boost the phase here, increase it by using that type of compensator. So I'm going to try to add this compensator here around somewhere here so that the phase here increases to a large value and we get a very large phase margin at the end. Okay? That is what we're going to try to do. We are going to add this phase here to the phase of the open or uncompensated system. But what is going to happen at the end is, unfortunately, that if I try to add this phase here, somewhere around here, this magnitude is also going to be added to the system. What is going to happen then? If I add this phase somewhere here, if I put the peak phase here, then this magnitude, this positive magnitude in dB scale, will unfortunately shift this magnitude as well. So this thing is going to shift here as well. Okay. So I will get a magnitude plot which is looking like this. So the gain crossover frequency of the system will also shift. Okay? And that is going to bring us additional phase decrease, unfortunately, in the system. So I have to be very careful in designing this type of system. Okay? So here we are going to try to benefit from the phase waveform here. We are going to benefit from this phase, but this magnitude is unfortunately going to serve as a side effect in the control design. Okay? We are going to try to overcome this side effect while benefiting from this phase increase from this phase lead compensator. So when we go into the so-called phase lag compensator, we are going to do the reverse. In that case, we are going to benefit from the magnitude, and then phase is going to be a side effect. So the roles will be reversed when we go into a phase lag compensator. So here, as I told you, since the phase margin of the system was 10 here, what I have to do, for example, my performance measure here, my performance requirement might be the phase margin. Suppose that I want the phase margin to be larger than or equal to 50. Okay? Then how much phase should I add by the phase lead compensator? The phase margin is already at 10 degrees. I need to add 40 degrees of phase margin. So that means that I want this maximum to be approximately 40. Okay? In order to be able to make this maximum 40, I need to know how to choose these parameters alpha. Okay? We're going to see that this maximum is going to be dependent on only the parameter alpha. Okay? By selecting the alpha value suitably, I will be able to get some maximum value here that I would like to add. Okay? But that actually means that I need to know the relationship between this maximum phase value and the parameters of the system. I will call this maximum frequency value as omega m and the maximum phase value as phi max. And there will be a magnitude here that is going to be added. Before here calculating these values in terms of the parameters of the system, alpha and t here, I'm actually going to be looking at what is this maximum magnitude value. Which magnitude value do we have here at the saturation of this magnitude saturation at this point? What happens if you let omega go to infinity in this formula? What does this transfer function become when I let omega go to infinity? It becomes 1 over alpha, so this point here is 20 log 1 over alpha. Okay. So now we are going to investigate what is these parameter values. Omega m, what is it in terms of alpha and t? Phi max, what is it in terms of alpha and t? And what is this magnitude at the peak phase here? What is the magnitude there of the system? So now let me try to find where the maximum phase is reached. I'm going to be looking at the phase of this GC of j omega. How can I calculate the phase of such a transfer function? What is the phase of the numerator? Can you give me a formula for that? Phase of 1 plus j omega t. That is the magnitude. I want the phase. Arctangent omega t divided by 1. Okay, so that is going to be just omega t. And how should I add the phase of the denominator? I need to put a minus sign. What is the phase of that thing? Omega alpha t. Okay, so this is the phase of the compensator, and I'm looking for where that phase is maximum. Okay, so what am I going to do here? Take the derivative and equate it to 0. So we are going to have only one point at which that derivative is equal to 0. So the derivative of the arctangent function what is this? Anybody remember? This is just this. It is just this. Okay? So it is 1 over 1 plus x squared. So if I take the derivative of this thing with respect to omega, okay? When I take the derivative 1 over 1 plus omega t squared, okay? Is this all? I need to write also derivative of the inside here. That is the chain rule. Okay? What is the derivative of inside with respect to omega? It is just t. Okay? Minus 1 over 1 plus omega alpha t squared, and here into the numerator I should write alpha t. Okay? That is equal to 0. So we see that here these t's are cancelling because they're positive. I can cancel. So I see that here 1 over 1 plus omega squared t squared is equal to alpha over 1 plus omega squared alpha squared t squared. So now making some algebra here, 1 plus omega squared alpha squared t squared is equal to alpha plus I have alpha omega squared t squared. Okay, so I can collect all of the omega terms on one side. So I can take 1 minus alpha here, and here I can take omega squared in the other terms. When this one goes to the other side, I can take alpha parenthesis 1 minus alpha omega squared t squared. Alpha value is between 0 and 1, so I can cancel this without any harm. So I can now extract what omega is. Okay, so omega squared is equal to 1 over alpha t squared, meaning that omega is 1 over square root alpha t. Okay? So this omega m, that is my omega m value. Okay? So here, this point where the phase reaches its maximum is 1 over square root alpha t. So here, the interesting thing is that this is just this. square root of 1 over t times 1 over alpha t. What is this omega n? It's not harmonic. It is the geometric mean of these two corner frequencies is where the phase makes a peak. Okay, that actually means that in an accurate plot here, it's going to be the arithmetic mean. So we're going to, in a logarithmic plot, it's going to be right in the middle. Okay, so this point in a logarithmic plot is going to be right in the middle because it's going to be the geometric mean of these two corner frequencies. Okay, now we're ready to find phi max here. Phi max is going to be given by just the substitution of omega n into that formula. Okay, it is going to be arctangent. When I substitute this omega m into that omega, t's are going to cancel 1 over square root alpha minus I have arctangent, and when I substitute omega into this term, then t's are again going to cancel, and I will get square root alpha here. So now, in general, what I would like to do is that, for example, I will want this maximum peak to be 40 degrees. Okay, I want this maximum to be 40 degrees. And in order to be able to have this to be equal to 40 degrees, I'm going to ask for the value of alpha. Okay? So in general, I won't want this expression, but I would want the reverse expression. Okay? I will want alpha in terms of phi max, because I will know what phi max should be, and then I will ask you what alpha should be. Okay? That is why I need to invert this expression, and I need to leave alpha alone. So here is what we are going to do. This is going to be my angle theta 1, and this is going to be my angle theta 2. Okay? So this phi max is therefore equal to theta 1 minus theta 2. Okay? Now I'm going to be looking at the sine of this angle. Sine of phi max is going to be the sine of this difference. And when I expand that difference, it is going to be sine theta 1 cosine theta 2 minus cosine theta 1 and sine theta 2. Okay? It is going to be something like this. And now I have to write this sine theta 1, sine theta 2 in terms of the value of alpha. So here we see that theta 1 is the arctangent of this ratio. So if I look at a right triangle here with angle theta 1 here, the tangent of that theta 1 should be 1 over square root alpha. Okay? This is 1 over square root alpha. So here the hypotenuse should be just this, square root 1 plus alpha. Okay? And theta 2 is the angle whose tangent is square root alpha. Okay? Theta 2 is the angle whose tangent is square root alpha. On this triangle, where is theta 2? This is going to be theta 2. Its tangent is square root alpha divided by 1. Okay? Then I can now look at what the sines and cosines of these angles are. Sine of theta 1 is going to be 1 over square root 1 plus alpha. Cosine theta 2 is 1 over square root 1 plus alpha. Minus cosine theta 1, it is square root alpha divided by square root 1 plus alpha. And sine of theta 2 is going to be the same as this one. Square root alpha divided by plus alpha. Okay? And this is going to give me the following. 1 minus alpha divided by 1 plus alpha. Okay? And I have the expression 1 minus alpha divided by 1 plus alpha is equal to sine phi max. And now let us distribute this expression. It is going to be sine phi max plus alpha sine phi max. Okay? And from this expression I can actually extract what alpha is. From this expression you will see that alpha is 1 minus sine phi max divided by 1 plus sine phi max. So given phi max here, I can know what the alpha value should be. And here the final thing is going to be to calculate this magnitude value at the peak phase. Okay? What is this magnitude value? For that, I'm going to substitute this omega m value into the magnitude of that frequency response. First of all, let us look at what that magnitude is. Magnitude of GC of j omega is the magnitude of the numerator is square root 1 plus omega t squared, okay, divided by square root. The magnitude of the denominator is 1 plus omega alpha t squared. Okay. When I substitute omega m into this formula, I'm substituting this thing. Okay. This is omega is equal to omega m, and omega is equal to omega m here. Let us substitute. I have square root 1 plus 1 over square root alpha squared. It is 1 over alpha given like this. And I have 1 over, this thing is going to give me 1 plus alpha. Okay. That is equal to, just, if you equate the denominators here, you are going to get 1 plus alpha divided by alpha here. So 1 plus alphas will cancel. So I will get 1 over square root alpha. Okay? That is the magnitude at that peak frequency. Okay? So here, this point is 20 log 1 over square root alpha. So we see that the magnitude the largest magnitude that we reach here is 1 over alpha, and the magnitude at the middle here is 1 over square root alpha. In a logarithmic plot, what should happen between these two values? This one is going to be half of this thing, because we see that this is 10 log 1 over alpha. Okay, you can take 1 over 2 outside the logarithm, and then that's going to give you the half of this value. Okay. So here these are the relationships between the parameters of the phase lead compensator and the phase and the magnitude parameters here. Okay. So now we're going to use these parameter expressions in order to be able to design our compensator. So here I can write my phase formula. So I have omega m is equal to 1 over square root alpha t, and I have phi max is equal to, I have 1 minus sine phi max, so this is alpha of course, divided by 1 plus sine phi max here. Okay. So now let us look at phase lead compensator design. So what do we mean by design here is the following. So I will have a control system and I will have a G of S here. The system does not have to be a unity feedback system. You can also have an H here. It doesn't matter. Instead of G, you can use GH in such a case. Okay? So this is the control system, and here we're going to add our compensator. Okay? So we will either know the transfer function G of S, or we will know the body plot of G of S. Okay? There are two things. If you know the transfer function of G of S, if you know actually its poles and zeros, then you can make an analytical design. That is called analytical design. If you know the explicit form of G of S, then that is going to be the analytical design of phase lead compensator. But sometimes you won't know what G of S is, but you will only get its body plot. That is what happens in practice. Okay? In practice, you have a system that you would like to control here, and you don't know anything about its transfer function. But you have made some experiments on the system, you have given some sinusoids and looked at what the phase shift and the magnitude change of the sinusoids, and you might draw the body plot of the control system. And then you won't know what the transfer function g of s is, but you will get its body plot. Then, based on the body plot, without extracting any transfer function from the body plot, you need to design your compensator. Okay, that is called graphical design. Okay, there are two different things that we're going to see here. We will first see the analytical design here when we know the transfer function g of s. But at the end, we will be able to design our compensator without knowing what g of s is, but we will get only its body plot. Okay? So here, what we're going to put here is gc of s. I will put my phase lead compensator here, and I will add also a gain k here. Okay? And on this control system, we are going to put some requirements, performance requirements. The first requirement is usually going to be a steady state error requirement. Okay? And the second requirement is going to be a transient requirement. And that is going to be given by a phase margin requirement. Okay? For example, in our first example, we are going to see that the first requirement is the following. This should be smaller than or equal to 0.1 to a unit ramp. Unit ramp input. This is the steady state error requirement of the phase lead compensator design. And we are going to require phase margin to be larger than or equal to 45 degrees. Okay? And this is going to be our transient response requirement. Phase margin usually determines the transient performance of the system. The larger the phase margin is, the better the transient response is. So this is the transient requirement of the phase lead compensator design. Of course, for each problem, these specific numbers might be different, but you would get both of them in general. So now, what do we mean by design? To satisfy these performance requirements, we need to find three different parameters. The first parameter is going to be k. I will choose what this k is. That will control the steady state error requirement. Okay? And then I will choose the parameters of alpha and t. Okay? What are these parameters, k, alpha, and t, to satisfy these performance requirements? Okay? That is the phase lead compensator design problem. Any questions here? So here, as I told you, we are going to be designing the phase lead compensator analytically. Then graphical design is going to be much easier. It's just going to be reading some values from the body plot. Okay? So here, for this example, I'm going to choose g of s as 2 over s plus 1. This is going to be the system that we would like to design the phase lead compensator. Okay? So we are going to go step by step. So I will start by step 1. So step 1 is find k to satisfy the steady state requirement. Okay? So here, this is the easiest task in the analytical design. So here, only k is going to determine the steady state error requirement. Okay? So let us try to see why. So here, the steady state error requirement is given for unit ramp input. Okay? For unit ramp, the steady state error is given as 1 over kv, and kv is the static velocity error constant. It is the limit as s goes to 0, the open loop transfer function. Okay? And the open loop transfer function for this example is going to be limit as s goes, so this is s of course, limit as s goes to 0, I have s times, I have k, I have gc of s, and I have g of s. Okay? So now, in this gc of s, let s go to 0. what do you get? You get just 1. So this is not really changing anything in the steady-state error performance because this is already in body form. So when s goes to 0, this goes to 1. Okay, so this is really not important in the steady-state error performance. Okay, so that actually means that only k and g of s would determine my steady-state error performance, and phase lead compensator does not change anything in the steady state. Okay. So here, what is going to be this limit if you use that g of s there? This s is going to cancel this, okay? And then I will get what at the end of this limit? Yes? It is just going to be 2k. So here I want the steady state error to be smaller than 0.1. What is the value of kV to get this value? What is the value of kV that I need to get that steady state error? Should be 10 here. Okay. If this is 0.1, then kV should be 10. Okay. And so here in our design, we are always trying to achieve these limits. Although this steady state error should be smaller than or equal to 0.1, we usually make our design to reach these boundaries. Okay, so we do not want to force system any more than we need to. Okay, that is why we always try to catch these boundaries, not anything more strict here. Okay, so I can try to substitute E steady state is equal to 0.0001, but that is going to give me a very large k value, which might force the system to be saturated at the end in actual control system. That is why we always try to achieve these boundary values and not go beyond that. So here we see that k should be 5. Okay, that is our gain value that we need to use.
Do we need to check if final value there holds?
In this case, we are going to make sure that phase margin is actually always positive. If I satisfy this requirement, phase margin is going to be positive. That is going to ensure BBOS stability. And when we have BBOS stability, final value theorem would always hold for the error signal as well. So we have obtained our k value. Now in the second step, which is actually very easy, step 2 is combine k and g of s. Okay? The combined system is called the uncompensated or combined system. Maybe I shouldn't write this. I'm stupid. So we will call the combined system the uncompensated system. It is uncompensated because currently GC of S is not included in it. Okay? That is why I will call this combination as G uncompensated of S. It is going to be K times G of S. In the lecture notes, you might see that this is called G combined of S. Okay? It is the same thing. G uncompensated is the same thing as G combined of S. And when I combine that gain K is equal to 5 with the system here, I will get 10 divided by S plus 1. Okay? This is our uncompensated system. Now let us look at step 3. Obtain a Bode plot of G uncompensated of S. Okay. Now I'm going to try to draw an approximate or asymptotic Bode plot for this system. For that, I'm going to substitute j omega there. So G uncompensated of j omega is equal to 10 over j omega times 1 plus j omega. The system is already in Bode form. If it is not, I will first bring it into Bode form, and then I will substitute S equals to j omega here. Okay? So now let us try to draw the magnitude plot for this system. This is my omega, and when I look at the phase, I will draw something like this. Maybe not here, a little bit below. So what are the corner frequencies of such a system? The corner frequency of this term is, it is 1 radian per second. Corner frequency of this thing would not count, it is somewhere to the left. Okay? And the only corner frequency is 1 radian per second, so I will put 10 and 0.1 here. When the frequency is much lower than the corner frequency of all terms here, when the frequency is, for example, 0.1, what is the magnitude? When frequency is 0.1, what is the magnitude of such a transfer function? When frequency is 0.1, this term is going to give me only 1. Okay? Because this term is going to be negligible. This is 1. It is 10 over omega. The magnitude is 10 over omega if omega is somewhere around 0.1. Okay? 10 over 0.1 is going to be 100. 100 in dB scale is going to be 40 dB. Okay? So I will have 40 dB here, and at 0.1 we're going to be approximately at that magnitude. What is going to be the slope there for low frequencies? For low frequencies, this term is negligible, so I will have a transfer function of like 10 over j omega. And the magnitude is going to be 10 over omega. If I look at this thing in dB scale, what is going to be the slope of that thing? Yes? 10 over omega, 20 log this thing. When I try to write this thing as, this is 20 log 10 minus 20 log omega. If I call log omega as x, okay, and if this thing is y, this is going to be y is equal to, I will have minus 20x plus this is 20. Okay? This is just a line with slope minus 20 dB per decade. Okay? So that actually means that when the frequency increases 10 times, the magnitude is going to decrease by 20 dB. Okay? So you would see it here. When the frequency increases 10 times, then this thing is going to be decreased by 20 dB. Okay? That is going to be the asymptotic approximation of the border plot there. When the frequency passes 1 radian per second, what is going to be the new slope? When the frequency increases the corner frequency of this thing, this 1 is going to be negligible. Then I would have 10 over j omega squared. Okay? And then if I look at the slope of that thing in a log plot, what is going to be the slope? Minus 40 dB per decade, meaning that if the frequency increases 10 times, the magnitude will decrease 100 times, meaning that the slope is going to be minus 40 dB per decade. So when the frequency increases, I will be here at minus 20 dB, okay? Minus 20 dB here. So that is going to be how my border plot would be looking like. Okay? So now let us look at the phase. So if I have minus 90 here, then minus 180 degrees here, what is going to be the phase of this thing as frequency goes to 0? The phase of this thing as frequency goes to 0. If frequency goes to 0, this term is not going to bring any phase. It's going to turn into 1. Okay? And then I will get, if frequency is small, I will get 10 over j omega, which has the phase minus 90 degrees. So the phase is going to start at minus 90 for low frequencies. And for very large frequencies, what is going to be the phase? For large frequencies, this 1 is going to be negligible, and I will have 10 over j omega squared. Each j omega is going to bring us minus 90 degrees. What is going to be the phase as omega goes to infinity? Minus 180 here. Okay, so at this frequency, I'm going to get this phase. And finally, what is going to be the phase if we are exactly at this corner frequency? So if omega is equal to 1, the phase of this term is going to bring me minus 45 degrees. And this is minus 90 degrees. So we're going to be right in the middle at minus 135. Okay? So the phase is going to be looking like something like this. Okay? So at this middle point, we have at minus 135.
Hocam, did we say 40 decibels because we neglected 1 plus JW count?
What do you mean?
How did we find the 40 decibels?
Okay. So if the frequency is 0.1, then this means that the frequency is at least 10 times smaller than the corner frequency of this thing. Okay? I will assume that around omega is equal to 0.1, 1 plus j omega is going to be approximately equal to 1. Okay? That means that this term is not there. You can think about it like this. Then when I substitute omega is equal to 0.1, the magnitude will be 100. Okay? So now this completed step 3. Sorry, step. Now, how many step please? Step 2, step 3. Yes. Okay. So here let us look at step 4. Find the gain crossover frequency omega g and the phase margin of the uncompensated system.
Do we do that analytically or from what?
When you have the transfer function, you can do it analytically, but in the graphical design, we will just check it from the body plot. Okay. So here, if you just look at this body plot, where is the gain crossover frequency? Gain crossover frequency is the frequency at which the magnitude crosses 0 dB. This is 0 dB. What is this frequency? It's right in the middle between 1 and 10. It is going to be the geometric mean of these 2 points. Okay? It is going to be at square root 10. Now let us try to do it analytically. So here, G uncompensated of J at the gain crossover frequency is going to be equal to 1. This is in linear scale. Okay? In dB scale, it's going to be 0 dB. Okay? So let me write the magnitude of this quantity. Okay? It is going to be 10 over magnitude of j omega is omega, and the magnitude of 1 plus j omega is going to be square root 1 plus omega squared. Okay? So this thing should be equal to 1 at the gain crossover frequency. Okay? That actually means that omega times square root 1 plus omega squared is going to be equal to 10. And if I take the square of both sides, I'm going to get omega squared, 1 plus omega squared is equal to 100. Okay? So when I try to write this thing as, it is going to be omega to the 4 plus omega squared minus 100 is equal to 0. The gain crossover frequency is going to be a root of this polynomial equation. Okay? So now I can calculate bazen böyle bir sınav sorusu falan oluyor. 4. dereceden bunu ölürüm de yapamam diye kalınıyor. Ona çok canım sıkılıyor. How can I find the roots of this thing? Just call omega square. Omega square is equal to a. Okay? Then this would be a square plus a minus 100 is equal to 0. Okay? Then if I calculate a values here, then it is going to be minus 1 plus minus, I have 1 plus 400 divided by 2. Okay? Which one I'm going to use here? There are two roots there. I'm going to use the minus sign or the plus sign. Why? A is omega squared. It has to be a real and positive number. Okay, so this minus sign is not really necessary. Okay? And if you would like to approximate this number, what are you going to give me? What is this approximately? Approximately 10. Okay? So we see that omega squared is equal to approximately 10. Omega is approximately square root 10, of course. Okay? So now what I have to do, then this is omega g, okay? This is the uncompensated gain crossover, this is the uncompensated system gain crossover frequency. Now what I have to do is to go below into the phase plot and look at what the phase is there, okay? But I know now the analytical gain crossover frequency, okay? And then what I can do is that I can substitute it here and find the actual phase of this system at that frequency. Okay, let us try to calculate that phase. G uncompensated of J evaluated at the gain crossover frequency omega G is given like this. The phase of this thing is minus 90 degrees because of the J omega term, and the phase of this thing is going to be minus arctangent omega. Okay? And omega here is square root 10. Okay? Then I have to calculate just what this thing is. And if you calculate that arctangent value, you're going to see that this is minus 90 minus 73 here. Okay? That is what arctangent square root 10 is. And this thing is going to give me minus 163 as the phase of this transfer function. So this point here is going to be approximately minus 163. What is the phase margin of the uncompensated system is that?
17.
Yes. So in this case, I can actually write here the following. Phase margin uncompensated is going to be this phase value G uncompensated evaluated at omega G plus 180 degrees. Okay? If I add this thing 180, then 17 degrees is going to be my phase margin of the uncompensated system. What can you say about the stability of the uncompensated system? Without this compensator, do you think this closed loop system is stable or not? Why? It has positive phase margin. Okay? So we know that the uncompensated system, even without the compensator, it is actually stable. So we are trying to work out or design our compensator only for improving the performance. I need to increase the phase margin to 45 degrees at least. Okay? So here I have the required phase margin. I have the uncompensated phase margin. The remaining phase is going to come from our compensator. Okay? So you now try to guess how I'm going to choose this phi max. I'm going to choose it as 45 minus 17. Okay? In general, I will try to add an error margin to that value as well. Why is that? Because when I add the remaining phase here, when I add this phi max there, if I choose my phi max, 45 minus 17 here, what is going to happen is that the phase here is going to come at the required value. But because of the magnitude here, the magnitude is going to increase and this frequency is going to shift to the right. There will be a decrease in the phase of the system. Okay? So if I choose my phi max as 45 minus 17 exactly, I won't be able to get at the end the required phase margin of 45 at the end. Because of the decrease in the phase of the system due to this positive gain here. Okay? That is why, in general, what we are going to try to do is that I will choose phi max to be 45 minus 17 plus some 5-degree error margin. Okay? So I will assume that that decrease is going to be less than or equal to 5 degrees, and I will add an additional 5 degrees there. But that is going to be in the second lecture. Let us give a break. 45 geçe tekrar başlayabiliriz. 45 geçe.
Başlarken şeyden bahsetmiştik ya. İşte bu sürekli gittiği zaman işte yüksek frekanslarla noise olur. Bu sefer noise olur.
Doğru.
Mesela şey yapsak böyle işte